Python VM using CHERI.
All right, thank you. Yes, and this work I did also with my colleague Dejice, who's in the crowd here, and Jeremy, who can't be here at the moment. So first, what is MicroPython? You all know what Python is. MicroPython is a bare-bones interpreter. It's designed for embedded situations, so it's optimized for code size, but it has full syntax of Python 3.4. It doesn't have all the libraries built in, but all of the syntax is there. And it is, of course, written in C, like so many interpreters and VMs. The more interesting question is, what is Morello? What is CHERI? So Morello is the CHERI prototype architecture developed by ARM. It's an extension to the Neoverse processor implementing ARM v2 8.2a. So 64-bit ARM stuff. CHERI itself stands for Capability Hardware Enhanced RISC Instructions. This is a set of instruction set extensions that allow certain spatial memory safety guarantees. So I'll talk a bit more about that, but basically converting pointers into a more sort of type-safe, memory-safe thing. You can use two roughly different APIs with it. So the hybrid API allows you to use mostly capability oblivious code, but run it within the environment that understands these capabilities. It uses some implicit privileges and a global register. You can also use the PureCap API, where your code is compiled fully aware of capabilities, and every pointer winds up being a capability, and it uses the full protection features. Morello capabilities, implementation of CHERI capabilities, they're 129-bit fat pointers. So you've got your address, which is basically your standard pointer, but then you also have metadata. So you have bounds and, over which the capability is valid. Any memory access has to be authorized by a capability, and a capability can only authorize access over its bounds. So you can no longer have buffer overflow attacks, for instance, provided that you make sure your capability bounds are set properly, which is something your compiler can often do for stack allocations. You also have permissions, so you can mark a certain capability as read-only, for instance. You've got an object type field that allows you to sort of seal capabilities to prevent them from being directly used, but then unseal them later if you have adequate privileges. You've also got a provenance tag, and this might be the most important bit. This is 1 bit stored out of band, so you can't access it directly in memory, and it tracks whether a particular memory region contains an actual valid capability or just a sequence of bytes. There's a guarantee of monotonicity, so anytime you want to create a capability, you have to derive it from an existing capability by narrowing the bounds or permissions. If you try to increase the bounds or permissions or otherwise do something that violates the rules of deriving capabilities, it will clear the tag, and a capability with a cleared tag cannot be used for anything. It just winds up effectively being an integer. As I mentioned before, the object type allows you to seal capabilities. The most interesting case of this is the sentries, where you can take a function pointer and seal it so that the you can give access to this sentry, and it will allow you to call that function, but only at the particular entry point. It won't allow you to jump to an arbitrary point in the function, and it won't allow you to read any of the function's actual code. So this has obvious protection implications, improve defense against return-oriented programming and things like that. It's important to note we have single source provenance, so each capability has to be derived from exactly one other capability. If you have, so you can't combine two capabilities together and be like, well, they're adjacent in bounds, so I want one big capability that covers them both. Each capability can only be derived from one other. Some implications. Our pointers are now larger than our, integer word types, which is something that a lot of C programmers would, not expect in most cases. You also can't just cast through a pointer through a long. If you do, it will result in provenance loss. So the capability tag and metadata will be discarded. And when you try to dereference your pointer after casting it back, you'll wind up with a tag violation because you've lost that provenance. The specific type uint pointer t and int pointer t it stores an integer, but as a capability, it actually preserves provenance. So you can use that particular integer type, but any other integer type is going to lose provenance. One implication of the fact that uint pointer t and int pointer t is a capability type is that you can't just tell the compiler necessarily to add two of the values together, because it doesn't know which provenance and metadata it should keep. So the compiler can't know whether you mean to add the sort of value of this capability to the whole first capability, or whether you want to keep the whole value of the second capability, and the whole provenance of the second capability, and just add the value of the first. We also don't have the same representable range that one would expect from the size of the uint pointer. So the uint pointer t only has the same representable range of integers as a long, despite being twice as wide in memory. But on the plus side, there are a lot of behaviors in C that are undefined and can lead to either memory corruption or, if you're lucky, a seg fault. Most of these wind up becoming replaced with a very predictable CHERI protection fault that is guaranteed to be thrown whenever you use an out-of-bounds access or an access without valid permissions or with a cleared tag. So some changes that were required to build MicroPython with the under this pure cap system. We had to change assembly somewhat. So where inline assembly was used to implement non-local returns, we had to change the registers so that the full capability registers were stored rather than just the integer registers to make sure that the stack was properly restored. We had to remove areas where uint pointer t was used where there weren't actually pointers being stored, because, like I said before, if you just try and add them together, the compiler will complain about provenance. Ultimately, you want to use traditional integers in as many places as possible, and only use the uint pointer t where you actually might store a pointer. So there were a couple of places where we had to keep uint pointer t, but for the most part, we swapped to explicit integer types, int 64t, whatever. But another interesting thing we had to change was there was a function that is involved in converting floating points to integers. MicroPython represents integers less than, I think, 2 to the 31 with a certain unboxed representation and with a low bit tag to make sure that it's seen as different from a pointer. And so the function to say whether or not it can be stored as a small integer relied on the size of a pointer to determine how many bits it had available, which is, of course, incorrect, because you can only use 64 of the bits to store the actual integer value. The rest is metadata. So we had to change that. We also had to create a new built-in Python type to hold the capability. There are places where you can pass a pointer from Python code through the libraries into your Python code, manipulate it, and then send it back to, into a native area. And we need to change that to a capability. We need to be able to wrap a capability, or else, again, we have provenance loss. In order to realize the advantages, the compiler can automatically set bounds on stack allocations in a nice way, but we need to tell our heap allocator to set explicit bounds on its the pointers that it allocates, because otherwise heap pointers grant access to the entire heap area, and that's not desirable. So we also need to rederive the wider bounds within our free or realloc in order to manipulate the stack data. So we have to be careful with the way we implement the free and realloc, we can't just assume, because we've now narrowed the bounds when we allocated, that we can't just assume that we can use that pointer to access other data. And in particular, when you in-place reallocate some memory, you need to return a pointer with wider bounds, which means you sort of need to rederive it from the existing heap pointer. This also means that even in places where we have guaranteed in-place reallocation, so the code is used in argument to tell the allocator to fail if it can't reallocate in place, if it would have to move. Often there, it will just check the return value for null and then discard it, or just success or failure. But because, again, the capability bounds are so important, we need to actually save those bounds back in. So there are places where code needs to be modified. Some advantages of all this: we exposed a few dodgy buffer accesses in the actual original code, and upstreamed fixes to the non-CHERI, the main repository for MicroPython. Some of these had to do with the failure to account for the padding in a structure when allocating memory. So one was a classic read beyond end bug in a string. And another was an incorrect rounding for buffer length. So, if you're trying to take 3/4 of something, but you do the integer division before the multiplication, you're going to wind up with truncation issues. This formula there can wind up as much as 2 bytes too short. And so, fixing the order of that. It's little things that are very easy to go unnoticed when you're allowed to access 1 or 2 bytes beyond the end in the vast majority of situations, and nothing bad will happen, but there's still the potential that bad things could happen. So it's better to tighten this all up with this the CHERI paradigm. Here's an example of a mitigated vulnerability. So on the left, you can see, and this is the original unprotected hybrid code. If we allocate 2 byte arrays on the stack, and then we can use UC types to take the address of one of them and create a new byte array at that address and tell it it's 2 to the 14 bytes long. But the original byte array was only 1 byte. So this is clearly unsafe, the fact that we can then access arbitrary offset, and in fact we can, as you see there, corrupt the value of the other byte array just by writing to the correct offset. This is clearly undesirable, but it can't really be fixed in the native paradigm without adding some sense of bounds to the pointers. It just gets complicated. But because in CHERI we have the metadata built into the pointers, if we try to do the same thing, although it will let you create the byte array and tell it that it's much longer than it actually is, when you actually try to access the illegitimate offset, you'll wind up with a capability bounds violation because you never extended the capability bounds. You can't. It's the monotonicity. And so that will always be a violation, and you can't bleed from one heap object into the other. As for tests, we managed to get the vast majority of tests working just as they did on non-CHERI systems. You might notice one test was failed in our PureCat build that wasn't in other builds. That has to do with a particular library dependency for the actual MicroPython interpreter that doesn't fully support all features in its CHERI port yet. But I think actually, as of now, we've gotten a fix, and that should be a nice 0 at this point. Performance is a valid question. A lot of times, that's the issue people potentially see with CHERI. It's great to have more security, but what's the cost? So after a few rudimentary optimizations, we managed to get the following performance. You'll notice our total time is between 1.5 and 2 times that of the hybrid version, the non-capability aware version. And that might seem high, but there are a couple places that likely comes from. First off, the Morello architectures capability instructions are, it's a prototype architecture. So the hardware could well improve. In particular, there's a known issue with the branch predictor in PureCap code on Morello, and that's expected to come down quite a bit. We've also got some other optimizations that we can probably do in our code. For instance, the elide certain software bounds checks now that we have these hardware bounds in place. But ultimately, if you want to hear more about the performance stuff, you can come to my talk at VMIL tomorrow morning, first thing, where I go into a bit more detail about the performance of all this. So as far as future work goes, one of the big, sort of holy grails of CHERI is compartmentalization. So we're currently doing work underway to create a compartmentalization scheme for the MicroPython interpreter that will prevent extension modules that are written in C from interfering with VM internals, and prevent native libraries loaded through the foreign function interface from interfering with VM internals. So these will allow you to use third-party code in a somewhat safer way, but prevent some potential exploits for poorly designed or malicious third-party libraries. Like I said, we can probably try and remove some now redundant software bounds checks and things. This will require a nicer handler for the sigprot, because currently we just sort of throw an OS error. The last sort of thing that we're looking at is MicroPython is designed really for embedded systems. And while Morello is currently a server-grade processor, but there are CHERI processors in the works that would be targeting embedded, so creating a freestanding implementation of the CHERI interpreter is an interesting place to go there. Thank you very much.
Okay, we've got time for a few questions. So I'll start. So in a lot of representations in runtimes, right, have 31-bit integers or 63-bit integers or whatever. But now we've got there's the extra tag bit. Could you see ways of using that to alter the representation if you're using a CHERI?
Absolutely. So I mean, that's not really removing software checks, but it sort of falls under that category of taking advantage of the extra information and extra security that CHERI gives us to improve things. So yeah, I absolutely think that we could move from taking one bit away from integers to just relying on the tag bit. There are a couple of issues you'd want to distinguish between a capability that has had its tag cleared because it's been manipulated invalidly from a real integer. If you can change types that way, that might cause problems, so it would require a bit more investigation, but it is something that we're hopeful about.
So how do you see CHERI and capabilities being extended or integrated into more runtimes?
Can you speak up? I couldn't quite hear that.
So how do you see CHERI and capabilities in general being integrated into more runtimes? Do you think they will modify the implementation, or eventually you will fall into a hybrid mode where the runtime runs inside a sandbox that is managed by CHERI?
Well, ultimately, in order to take full advantage of CHERI, it is necessary to modify some of the code. The code necessary to be modified just to get it to run on a CHERI system, for instance, under the hybrid ABI, is minimal. But in order to take full advantage of the security guarantees, there are certain, like I laid out, source level changes. I don't expect those to necessarily change, but as new software is developed, and developed with better principles, you can wind up with less areas where you need to change things, because ultimately most of the changes you need to make come from assumptions about undefined behavior that never really should have been made by the original programmers, but were anyway.
Thanks.
Okay, time for one more question if we have. Okay, let's go for lunch, right?